Okay, great. Hello, everyone. Thank you for joining us today for our final speaker of the Design++ seminar series that we host every semester. And today we're happy to welcome Armeni as our speaker. I will keep this short, but if you want to look online on our website or on our YouTube channel, you can see all of the past events, past talks. And if you want to give a recommendation for a future talk or also be a speaker in a future talk, you could contact Michael or I. And for today, I would very much like to introduce our speaker. So Iro will give a talk on spatial-temporal understanding of the built environment using visual data. And for those of you who don't know Iro, Iro Armeni is a postdoctoral researcher at ETH Zurich at the departments of civil engineering, as well as computer science. So she is interested in the interdisciplinary research between architecture, civil engineering, and also machine perception. Iro completed her PhD at Stanford in civil engineering, as well as a minor in computer science. So prior to her PhD, she received a Master's of Science in Computer Science at Ionian University. And mechanical engineering, is it M engineering? Masters of Engineering, architecture and digital design at the University of Tokyo, as well as a diploma in architecture engineering at the National Technical University of Athens. And in the future, Iro will be joining the Civil and Environmental Engineering faculty at Stanford as an assistant professor starting next year, September. So with that, we're really happy to hear your talk today, Iro. I will stop share and the floor is yours.
Thank you, Danielle. Do you want to turn off your mic? Perfect. Hi, everyone. Thank you for being here. I'm sharing my screen for the room behind, as you can see, and I will now be sharing my own. I cannot share my screen. So today I will tell you about a project that has been taking me more than 2 years to complete. And I will tell you all about the challenges and the hardship and the results that we had with that. I can share now. Cool. So you can see my screen. Let me put it in presentation mode. Okay, here we go. Make this small. Okay, so as the title says, I will be discussing about how we can understand our built environment and its spatiotemporal dimension using visual data. And specifically, I will refer to this project, which is called Nothing Stands Still, and we are in the cusp of publishing it, and it's about a spatiotemporal benchmark on 3D point cloud registration under large geometric and temporal changes, and below you can see the author names that are part of this paper, all the people that put some effort one way or another into this. Many of these terms might be unfamiliar to you right now, but I will be introducing them throughout the talk. Most of you must be familiar with construction sites and how as the construction happens, we tend to add a lot of different materials, a lot of different elements in it, essentially a lot of information as time progresses. So we start with a space that is almost empty and we start adding insulation, wall panels, pipes, air ducts, electrical cables, etc. And all this information is very relevant to our sustainability goals and the circular economy goals that we are having, because with this information, we can actually understand what we are building in our built environment, where things are located, how are they connected with other elements, what are their attributes, the other kind of relationships, etc. So how can we get this information in a way that afterwards we can use it for other downstream tasks, such as the ones I referred? Now, the common practice would be to have a construction timeline of everything that happens in your construction site. And specifically, one would go and get a point cloud, a laser scan of the construction site, and so at time t, would you get at one temporal point how your construction site looks like. And all these red dots that you see on your screen are essentially laser scan locations where you place your camera inside this, this big space. We are talking about a laser scan that is tripod based. So it works by being put on a tripod and rotating around itself. And then at temporal time t+1, you will get another point cloud that shows the progress, and at time t+2, etc. And now the problem here is that we would like to be able to make associations, spatiotemporal associations across this data in order to be able to really understand what has happened, how things are connected, what has changed. Essentially, you would like to understand, you can see my cursor, right? Great. That this corner of the space is the same as this corner over here and this corner over here, and essentially for every other point on this point cloud. Now, the problem will become easier once we are able to align these scans in the same coordinate space, something that does not come out of the box when you're using these laser scan technologies. They can be placed in their own local coordinate system, which might not be the same for the different point clouds. But how can we solve that without using any kind of markers or georeferencing information? So just out of the box being able to do this. What I have to say is that this problem is non-trivial. First of all, because we are talking about spaces that showcase this large geometric appearance and topology changes because they're construction sites, right? So in a very small temporal point, temporal duration, like even within a day, you can see very drastic changes. In addition, you're not always capturing the same area again and again. For example, some parts of your construction might not be accessible to you because of some other kind of work, or maybe they laid concrete and you cannot step on this part of your construction. And finally, there are some deformities that occur while you're creating at one time step the point cloud, which might be different in another point cloud in another temporal step, which means that even if you're looking at the same kind of geometry at one temporal stage and another, they might have differences. So how do you deal with these things again when you want to align these in the same coordinate system? So let me start introducing some of the terms that I discussed at the title. And we are talking about the task of spatiotemporal 3D point cloud registration in terms of computer vision, which is essentially what we want to do: align the different temporal points, the different temporal stages, the different point clouds for the temporal stages together in the same coordinate system. Now, how this task works is essentially, given these two point clouds that you see right now on your screen, from time t and time t+1 is the same stage, just changed over time, the same location just changed over time. You want to find pairwise correspondences from the static parts of the scene that have remained the same, and ignore the temporal changes, because these are points that you're not going to be able to align things together afterwards. Let's look a little bit into prior work. And we have to look into two things in order to perform this task. The first one is there any data set out there that we can use for solving this task of spatiotemporal point cloud registration under the large changes of geometry and appearance and topology we discussed? And the second one would be, is there any method that we can use? If both of them exist, then we can see how to improve a certain method, or if the task has been completely solved, then we don't need to do anything. Spoiler alert, a lot of things don't exist. So that is why I'm going to continue this talk and not stop right here. In terms of spatiotemporal 3D point cloud datasets, most of existing work has to do with small scale spaces up to a room or maybe a couple of rooms. And it looks at how they change over time in occupied spaces, in apartments, in maybe offices, but not in the scale of a construction, not in the time of a construction. Also, it looks into change that has to do with addition, removal, or relocation of a certain furniture inside a space, like a chair moving around and maybe removed from the room, but it doesn't look at these drastic changes we are referring to. So this means that we are in need of a data set that showcases what I've discussed so far. As for methods, there are several methods that exist into solving the spatial registration, essentially looking into how can we align two point clouds that have been taken from the same space together to form one coherent point cloud. They don't really look into the temporal dimension. Some work can be found in the self-driving car community, because as you understand, as a car moves, it will take several data points, several point clouds that have some temporal aspect into them, because the car is moving, time progresses, so there are some changes. However, these scenes are mainly static, which means the road will be there a few seconds later, the buildings will be there a few seconds later, the trees. What might have changed is maybe some cars and maybe some bicyclists, but the main geometry of the scene remains unchanged. So it is unclear if these algorithms that can solve spatiotemporal registration in the self-driving car community can also do it in the construction site. Let's find out. In order to address these aspects, we created this work, Nothing Stands Still, that introduces a data set of construction sites, which I will discuss in a lot of detail in the following part of this talk. It is a benchmark, so we're going to look into existing algorithms and how they perform to solve two tasks: the pairwise registration, which is this one over here, and the multi-way registration, which is this one over here. And I will discuss in a second what each of these mean. Okay, now we see a blown up diagram over here where I can discuss in more details what I just referred to. So the input to an automatic method, and I say an automatic method because we will be benchmarking existing algorithms, several of them, to see how they perform on this data set, is two individual point clouds. I will call them fragments from now on. And this could be from the same or different temporal points, but what they should have is some spatial overlap, small or big. The automatic method processes these 2 points and performs the pairwise registration, which means is aligning these 2 fragments together. Once we align all the fragments we have together, each with its own, right, we are going to perform multi-way registration, where we take all the fragments we have and we register it together to create a spatiotemporal map, essentially. So these are the 2 tasks that we were going to solve. If anybody has any questions, they're welcome to either raise their hand. Daniel, can you monitor that? Good. Or in the room, you can also raise your hand. First chapter, capturing the data. We collected point clouds, laser scans from 6 construction sites over several months in order to see how they progress over time. Now, this is more or less the scale that we are talking about, and please notice that we're talking about construction sites where we have the outer shell constructed, as well as the different slabs and different floors between the floors, but we are looking into monitoring the interior construction. So inside is a tabula rasa that we want to start putting rooms, etc. Here you can see a close-up of one small part of a construction site for construction A, B, and F, and just see and notice how many changes we're talking about, and see how from here, that is almost empty, we are going to do something like this, where we have already studs and insulations and machinery around and material all over the place, to something like this, where it's going to a more finished result, and machinery has moved, material, etc. So we are really talking about spaces that demonstrate large geometric appearance and topology changes. I will give you some close-ups of these construction sites right now, so that you have an understanding of what kind of data we are dealing with. So we're looking here into 2 temporal stages that are stage 1 and stage 3. There is also stage 2 somewhere in between. And if you look here a close-up, you can see how it's really an empty space. And by stage 3, it is full of machinery, ladders, materials laying all around. And if you look at this side, you see that you started with something completely empty, and you end up with rooms and almost doors and windows, etc. Here's another example, stage 5 and 6 for this specific floor plan. And we see again how at stage 5, we have some kind of structure for this space, but at stage 6, we have already created all the walls. We have even added all the static furniture that will exist in this space. Similar here, you can see how this was mostly an empty space, and suddenly we added all the installations that we had to with respect to this. It is actually a lab. Okay, so you saw a couple of examples. The capturing process was going around with a device that I will talk in a second. We were in contact with the project manager, and we would capture a point cloud every time there was information that would be hidden behind other surfaces. So every time there would be a panel on top of an installation, we would go and capture that. So we had to be in contact with the project manager. We didn't do it, let's say, every 2 weeks. How do we generate the data set? How do we get from these point clouds that we've created the fragments in order to perform the pairwise and the multi-way registration? Chapter 2. Now, we used the Matterport camera to perform these scans. And the main issue with the Matterport camera is that it doesn't give you access to the raw data. So it only gives you the final results that you see over here. Please notice that I have removed the ceiling for visualization purposes. There is a ceiling that exists as well for these spaces. So it just gives you the final aligned results. Essentially, all the fragments for this space are all connected together by their own software. I had made a kind of a spoken agreement with them that they would give me the raw data, but a couple of years passed or a year passed since I asked for it. And so they couldn't share it anymore since their company structure has changed a lot, and they decided that now they couldn't share this data with me anymore. So we had to find a different way to generate these fragments. So we went with simulation. Given the underlying 3D reconstruction and 3D mesh that we had, we're going to generate and simulate these fragments. And we're going to follow more or less the same way that the Matterport camera would work in terms of how far it can sense, how much noise it has, etc. So given, let's say, these 3 floor plans for the same construction, we're going to first generate an occupancy map. Essentially, it's a 2D floor plan where for every pixel on this occupancy map, we have a binary value. Is it 0 or 1? Is it white or black? Black would mean that there is an obstacle. White means free space, you can place your camera. And then we thought of how really scanning works. And usually you wouldn't find your camera tucked next to a wall, right? You wouldn't just put your camera next to a wall. You want it in between obstacles as much as possible to capture a lot of information. So we created a probability map that tells you the wider the pixel, the higher the probability of me placing the camera, the darker, the less the probability of doing that. And given this information, we sampled many, many, many locations, all those little red dots that I hope you can see on your screen. So we're talking about a lot of scanning locations. And the distance between them is between 1 to 2 meters, because for the Matterport camera, about 2 meters would be more or less the cutting threshold in order for you to actually connect the fragments together. So this is kind of the Matterport camera's suggestions of placing the scanners, the scans. Okay, so now we have a lot of red dots. Let's try to somehow find pairs of these dots to use in our data set. Oh, first of all, sorry, we need to simulate the point clouds. So we have these red dots. Let's see how we can get a point cloud from each of those, like essentially create the fragment. We used simulation, as I said before, and not only did we simulate exactly what exists in the underlying mesh that Matterport gave us, but we're going to add some noise to it. Because Matterport uses prime sense sensors, or less the Kinect type sensors, RGBD cameras. We only care about the depth here. And they are placed in this kind of orientation and location. So one looks straight forward, one looks a little bit to the top, one a little to the bottom, to have as much as possible coverage of with one rotation. And you can see something like that, where this is essentially the camera setup, and it will make a full rotation around itself, and it will stop 6 times to capture images. And then we simulate, as I said, with statistical noise that is given in the literature for the prime sense sensor, the depth images that it would capture, and then we stitch everything together into a depth panorama, which you can very easily extend into a simulated 3D point cloud. So this is how we get the fragments. And you can see here an example of how this point cloud would look like for this particular location. Okay, now we have all the possible scan locations we can simulate. We can also simulate point clouds. Let's find a way to create pairs. And now I want you to think that we are talking over here about learning algorithms, which means that we would like to have a distribution of fragments, fragment pairs that is as general as possible given the data we have. I mean that we would like to see easy examples and hard examples, and as much as create a distribution that is very uniform, instead of having what is called a long tail distribution, where centered data points are very badly represented inside the data set. The reason for that is because we want our learning algorithms to be able to generalize as much as possible to unseen data points beyond the data set we have created. And such a uniform distribution that looks at many different cases can lead us towards that. Okay, now, in order to create those fragment pairs, we decided to use 3 metrics that will allow us to understand the distribution better. The first thing we're going to use is the overlap ratio. This is a metric that is given from the literature and essentially tells us how much 2 point clouds, be that temporal or non-temporal, I say from different temporal points or the same temporal point, how much they overlap spatially. And it's given by this equation over here. And in the literature, it ranges from 10 to 80%. 10 to 30% is considered a very hard case, 30 to 80, and the more you go towards the 80 is considered an easier case. We also devised a new metric. Since we are talking about temporal changes, we want to make sure that our data set includes parts, fragments, where in the overlapping region, they have a lot or less changed points, right? We want to make sure we capture all possible easy and hard cases. And I will show here an example of these 2 cases. So with white and blue, you can see the yellow and blue, you can see the different fragments that we're supposed to be aligning together. The green points are in the overlapping region, and the red ones are also in the overlapping region, but have changed between these 2 point clouds. And now, when we compute the overlap ratio over here, OR, we'll see that it's the same for both point clouds, for both pairs. But if we compute the temporal change ratio, we'll see that in the second case is way, way larger, which means that in this particular scenario, more than 50% of the points have changed over time between these 2 temporal stages, which also means that, as I mentioned before, as I defined before, we want to find pairwise correspondences from the static parts of the scene. So suddenly you have less than 50% of static points that you need to choose correspondences from. And please also note that if we have flat surfaces, it's very hard to identify a correspondence. Correspondence is supposed to be a point inside your point cloud that is very distinguishable, such as a corner or some other kind of feature around it that allows it to be distinguishable with respect to any other point. A point on a flat surface doesn't get distinguished really from the one next to it or the one above it. And finally, the final metric we computed is that of geometric complexity, just to make sure that we have point clouds, we have pairs of fragments that can be very flat or very bumpy, like have little things, maybe it's just floor and wall surfaces, or have a lot of things going on in there. We computed all of them for all possible pairs. We created their distributions. We sampled them evenly, and we ended up with a data set, which I will explain in a second. Before I explain more, how are we doing on time? Okay, I want to discuss about the chicken and egg problem. Now, is the issue about the ground truth. As we are trying to solve the spatiotemporal point cloud registration problem, note that we have the same issue as I discussed before. When you're getting these point clouds from any kind of device, they are not aligned the same coordinate system. They don't give you this ground truth information. So essentially, we have to create our own ground truth. So we used algorithms that exist out there in order to align the big spaces together, the entire point clouds of the scenes. And of course, there are going to be deviations, as I discussed before, but we get the best solution that we can with a little bit of manual refinement. We almost get something that is very, very good as ground truth. However, there is an issue between local and global accuracy. So this ground truth that I say over here that we do with this algorithm and then with some manual refinement works perfectly fine for the multi-way registration step. But what about the local over here, the pairwise registration? Because of the way this global scan has been formed, there might be deformations between different parts of the scans over time. So a floor maybe in one temporal point might be a little bit like this, and the other temporal point may be a little bit like this. But we're talking about the same floor. That just because of the global optimization that took place, they have been deformed. So how can we deal with that? Because if we keep for the pairwise registration, which is something very local, the global ground truth, we're going to end up with giving false information, false ground truth data to our algorithms, and we will not really know if they can do good or not. So to address this step, we had to consider creating a different ground truth for the local step. How we did that, we found a cylinder inside this space. We cut like big cylinders things, big cylinder crops that that theoretically, when we are going to perform the same step as here, use this algorithm, iterative closest point, and some maybe manual refinement, but mainly just the algorithm, will give us the best possible local ground truth. Now, how do you choose the radius of this cylinder? Because if it's too small, and we're talking about also temporal scans, right? You might not be able to register it well together. If it's too big, again, you might have these deformities coming in. So we sampled different cylinders of different radius. And you can see here from starting to from 2, 4, 6, 8, blah, blah, blah meters until 20 almost. And we found that the one that is at 12 meters performs the best, which allows to have, based on the previous global ground truth, the smallest displacement. This means that it slightly fixes the error without really creating issues that would force these two cylinders to be really misaligned with each other. After we did manual inspection to many of the samples, we actually saw that it was doing a better job. And even in the cases where the errors with respect to the pseudo ground truth were high, even in these cases, it's actually doing a very good alignment. So this is what we went with. Here you can see some more examples. The GIFs are a bit fast, so it takes time to really understand. But believe me, the 12 meters is the sweet point for the entire data set to create this local ground truth. So we went, and for each fragment pair, we got the 12-meter cylinder radius, we registered it together, and we used that as the ground truth information for the pairwise registration task. Chapter 4, pairwise registration. So now we have the data set in our hands, we have to perform the task. How are we going to split our data set? Like, what are we going to use for training? What are we going to use for testing? We followed first what is usually used in the literature, which is the original split. Whereas, as I say, we train and test across all areas and all stages, which means if these are our 6 areas and these are all our temporal points, the big, essentially, point clouds, we're going to do some fragments for training and some fragments for testing from this same, essentially, area. We also thought that this is not enough to tell us how well algorithms are doing in the dataset, if they can generalize or not. So we also had another split, which is the cross-area split, which means that we're going to train on all data we have for 3 of the buildings that we've scanned, and we're going to test to the other 3, which is going to tell us if they can generalize to unseen data points. And finally, we have the cross stage, where our goal here would be to understand if an algorithm that has seen the first few parts, first few stages of a construction can generalize to the next few stages of a construction. This is exactly what this does. Today, I'm going to focus on the original task, while the other 2, you'll have to see the paper, because otherwise I would be here today talking about this entire paper. So, the original task. Before I explain how well the methods did, I need to tell you about the main metric that I will be presenting. We have more metrics in the paper, but today I will be talking about the registration recall. We're given all the fragments that we have over here. So each point is 1 fragment pair. We are going to measure how many of them have been found to have a correct alignment. Within a deviation of 0.2 meters. This is all standard for the literature. And so let's say from the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we were able to do 7 out of 10. Okay, this would be the metric. Let's go into the methods finally. And we benchmarked these methods that you see right now on your screen I'm not going to go into details about this method, but I can tell you that this uses handcrafted features, so no deep learning, whereas the rest use deep learning approaches. And going from here to downwards, we're talking about very state-of-the-art methods that use some what's called attention mechanisms to better understand the interaction between the fragments in order to best align them. You see that the pairwise registration for Predator, which is state-of-the-art and very top in many of the data sets out there, is topped to 65%. So this is the top accuracy that they can give. When you consider that in other data sets that are non-temporal, only spatial, it is able to achieve, even in the hard cases, more than 75%. So suddenly we see that it struggles in this particular setting that we are giving it. Now, this is not enough to understand how well the algorithms are doing for spatial and spatiotemporal cases. So we ablated the results. And you see here the performance of each of these algorithms for the non-temporal case, which means fragment pairs only from the same stage, and temporal pairs, which means only from different temporal points. And as we expect, the algorithms are performing very well in the non-temporal pair case, but they're particularly struggling in the temporal case, which you see, we start from almost 0 and we go top to 30% of registration recall. So for the best case, out of the 10 pairs, we do 3 well. And this tells us that the spatiotemporal registration, it's a very hard task, that we need better algorithms to be able to solve this, because our current algorithms, no matter how state-of-the-art they are and how well they're able to do for the same temporal case, they really struggle for the other ones. Here are some results, which are going to go fast because I do want to talk about the multi-way registration next. This is, again, pairwise registration in the original split, non-temporal pairs, which means for the same stage. And so you can see here, T is the translation error, R is rotation error with respect to ground truth. Here is source, target, the 2 fragments. And here is how these 2 methods are able to align the point clouds. And here you can see how it should be aligned. I'm not going to go, this is also a hard case with overlap less than 0.3. I won't talk into more details about those. Here again, non-temporal pairs with a medium overlap and a very easy overlap. Although, this algorithm is even struggling to do the easy overlap over here, you see how the translation error is more than 1.5 meters and the rotation error is almost 180 degrees. And also in the temporal pairs, again, with a very low overlap, we see that methods are struggling to achieve the ground truth alignment. And with medium and high overlap, again, we see that not always they're able to perform what they should, even though they have enough points and enough discriminative points to actually perform this, which means that still there is a lot of work to be done on the pairwise registration case. This is the registration recall for essentially the SDF plots, cumulative distance functions, for the different splits of the data set and for same and different pairs. I don't want you to focus right now on the plots, but I will tell you 3 things that you can take away. That the higher the overlap ratio, the better the performance. Makes sense. You have more area to look at and more points to find. Cross area is the hardest data set split, the one that is trying to generalize to unseen areas that's never seen before. And in all splits, no matter if it's cross area, cross stage, or the original, methods struggle with registering temporal pairs. This is the takeaway. We also had to see how well these methods are doing to other spatiotemporal datasets, the ones I referred in the beginning, that look into how normal spaces, occupied spaces of houses and offices that change over time. So how well these methods can solve the spatiotemporal registration task in this case. So we generated data in a similar way as we did for our dataset. This is specifically the 3R scan dataset. You can see here some differences, some comparison. And here you can see how the 3 top methods are doing with respect to non-temporal, temporal, and all pairs. Just notice this. Notice how big is the difference with respect to our data set. how this method is able to achieve 60% overall for the 3R scan data set, and in ours 20%. Here, Predator is able, which was doing the best in our data set, is able to achieve around 85%, and in our case, 65%. And believe me, 20% of a registration recall drop is very high for this kind of methods. And from this one that was doing 47, we are down to 39. So really, this shows that this data set is relevant also for the computer vision community, not only for people who are in the AC industry, in order to solve this spatiotemporal task problem, which is something that appears more and more now in our considerations, because our world is changing. We cannot just consider a static version of it, right? We have to consider the temporal aspect in it. Chapter 5. And last, multi-way registration. So I discussed before how for pairwise registration, we can have different temporal pairs that we need to align together, or same stage pairs, which again, we align together. Now in multi-way registration, we want to get all of these pairs and register them together into one coherent map. The way that you would do that is you would create a pose graph. So each node is one fragment, and you are connecting nodes together that you have information about how they're aligned from the pairwise registration step. So this over here is initialize this edge in the graph with this information for the pairwise registration. And the goal here would be to minimize the root mean square error of how these two are aligned together. But please note that this is a different objective of how the learning methods in the pairwise registration work, because they are trying to increase the registration recall and not minimize the root mean square error, which is a very different objective. And as such, you will see some issues in this assessment, which means we should also consider how can we create methods that are actually solving the same objective and not having them solve different objectives. So these are how these graphs look like. So here you see all the pairs for this specific building over time, and you see that they're connected together with edges when there is an exchange of information to happen. So we're talking about very, very big graphs, right? Here is another example with more temporal stages, and you see how these are connected to each other. You see that there's in some areas we do not have, it's because this is the test set, not the training set. So we don't have all information for everything. So some of these might be in the training set that you're not viewing right now. Now, in order to perform this pose graph, we need to, the method that we use, there's one main method that is doing multi-way registration. It needs to know how these pairs are connected together as a sequence, essentially. Imagine like a video, right? As a sequence of point clouds, one after the other, which is information we don't really have for our data sets. It wasn't captured with a video camera or a video scanner. And that is why we found that we can recreate that by computing a minimum spanning tree that will allow us to define these edges that are necessary in order to perform the pose graph optimization. Not going into more details. I'm happy for anyone who wants to reach out to me and I can describe more information on that, or we can also wait for the paper that will be hopefully coming out soon. And now you will notice here how methods are performing before the multi-way registration and after multi-way registration. You will see also that these numbers might be a bit different than what you saw before, because now the test set is a little bit different than for the one in pairwise registration, but essentially it's the same thing, just maybe some pairs are missing or some are added. So we are talking here about a 67 almost % registration recall and 40% before. And once we do the optimization, we get these results, which just focus over here. For the case of Predator, we can't really increase the results. We are usually the same or lower, as you will see in a second. But for GeoTransformer, we are really, really adding over here a lot of value, a lot of registration recall. And if we ablate these results, in order to understand how this is performing for non-temporal pairs and for temporal pairs, we will see that for the non-temporal case scenario, we cannot increase Predator, we're actually lower. We still increase quite a lot for GeoTransformer. What is interesting is in the temporal pairs, we have almost no significant value for Predator, but see how we have more than almost 7% registration recall improvement for GeoTransformer, which means that different methods will react differently also to this particular task. And this brings me to the end. I'll just want to remind a little bit the value of having this spatiotemporal registration task solved, because it can provide us a timeline of as-built information, essentially a documentation of how our buildings look like over time. And this can be used particularly for sustainability and circular construction, circular economy goals, because now you know exactly where things are, when they have been located, how they looked like before you start maintaining or recycling or reusing any kind of this information. It also can enable construction progress monitoring, which with some next steps I'm working on, it can actually do quantifiable progress monitoring and better quality control, because you have this underlying geometries and information in your hands. So my next and ongoing actually steps are, first of all, to perform the spatiotemporal 3D registration with our own method that can both address pairwise and multi-way registration with similar objectives and perform better than state-of-the-art methods right now. Also, I'm in the process of semantically annotating the dataset, so providing also semantic labels, such as this point belongs to a floor, to a scissor lift, to a pipe, to an insulation, etc., in order to really tackle this quantifiable progress monitoring or this documentation of knowing exactly what elements exist where in an automatic method. And finally, I would like to be able to solve the task of automatically creating methods that can perform the spatiotemporal registration by also incorporate joint estimation of semantic information. So jointly be able to align point clouds together, as well as predicting the labels of the objects that exist in these spaces. This is all ongoing work, and hopefully in the next year or two, I can have results on these things as well. That is all. I want to thank again my collaborators for this big project, and I'm happy to take any questions if you have. Okay.